All right, recording's resumed. Here we go. All right, so you guys ready to learn about theory of relativity? All right, this might be your one shot to learn about this. Guys, everybody look up here. I want you guys to learn something cool. All right, so we're gonna go back to 1849 when the speed of light was first pretty accurately measured. Now, it was a question for thousands of years, like what is the speed of light? It was assumed it probably had some discernible speed, or maybe it was infinitely fast. It isn't, by the way. It has some finite speed. Actually, if you go back to, I think it's the 1600s, I think there was an astronomer, his name was Old Romer, I want to say, something like that, I think Danish guy, who was watching moons orbit Jupiter and realized that when the Earth was kind of headed towards Jupiter, that frequency increased a little bit. When Earth was kind of headed away from Jupiter because of orbital paths, that frequency decreased a little bit. He was able to sort of estimate the speed of light, not super badly, but what you're looking at right here, 1849, it was actually like accurately calculated within about 2% of its modern understood value. This is a fun one. Like, you can do this with just rotational mechanics and just physics that you've learned in this class, AP. Now, it's a complex problem. You have to think pretty deeply on it, but I'll explain how this works. So let's say you have a light source represented by this candle, and you have a mirror way off in the distance, maybe several kilometers in the distance. I think he did this in Paris, and he had like several kilometers, like 5, 6, 7 kilometers, something like that. Okay, and he has this toothed wheel. Now, here's the observer represented by an eyeball. He's looking through the gaps in the teeth, and he sees the reflection of this light source, this candle. Okay, so that's all fine. That's all good, right? Okay. Now, what if he starts getting this cogwheel spinning, and it spins so fast that any ray of light that would hit a tooth never makes it to the mirror in the first place, so obviously you wouldn't see the reflection. But any ray of light that makes it through the gaps comes back so that this thing is just rotated a little bit. You guys see that little sliver of an angle, maybe just like a few degrees, so that this tooth covers an adjacent gap. And this observer also does not see the reflection. If you can get it spinning that fast, right? You guys can imagine that? If you can get everything to align just correctly, then if you know how fast you're spinning it, you can do a little bit of math and figure out what's the speed of light. The speed of light is lowercase c. You guys know that, right? And anyway, here's kind of a derivation how you can figure. Okay, so we figured out the speed of light. Now, modern day textbooks, you open it up, it usually says like 3 times 10 to the 8 meters per second. It's like 2.997 something. All right, anyway, 10 to the 8 meters per second. Okay, so great. We've known since 1849 what the speed of light is. It's crazy fast. Okay, it's like the limiting speed limit in the universe. Okay, all right, let's fast forward a little bit, a few decades. This Michelson-Morley experiment. Now, the premise of this experiment is they're thinking, well, we know something about waves. We know that sound waves, for example, need a medium to propagate through, right? Like if there was no air in this room, you wouldn't be able to hear me, right? Or maybe feel the vibrations of your desk, but yeah, but you need a medium for sound to travel through. And they were thinking, okay, well, that's true for pulses on ropes. That's true for, okay, that's probably true for all waves. That's what they're thinking back in the 19th century. So it's probably true for light. There's probably some medium that light travels on. Like, how does light energy get from the sun to Earth? Well, it's probably not air. So they call it luminiferous ether. See where I put in quotation marks here, luminiferous ether? Now, if you've never heard that term, if you've never read that in a science textbook, that's probably a good thing, because this experiment here that I'm showing you guys unintentionally disproved this concept. They were looking for this luminiferous ether. They think, well, okay, light probably travels on this. That's probably the medium it needs. And oh, you know what? Whenever I teach this in my classes, again, I'm giving you guys a shortened version of this. I usually have like a race. It could be a foot race. It could be a boat race. Here, can you guys just imagine in your heads? You guys are imaginative people, right? Let's say there's a lake next to a river, right? And there's 2 people in boats, and they say, hey, let's paddle down to that tree and back. So we're traveling the same distance. But one of us is going to travel on the lake where the lake water is not moving. One's going to travel on the river where we're partially traveling with the current, and then we go back and we're fighting the current all the way back. Okay. Now, who's going to win that race? The guy in the lake or the guy in the river? It's not the same. Somebody does win that race. Who says the guy in the lake wins the race? The guy in the lake. Yeah, you're right. Okay. Because the guy in the river, he might have, he might reach the tree, the halfway point, really fast as he's traveling with the current. But when he's fighting the current, anyway, if you run the numbers, if they're like equal rowers and equals, blah, blah, blah. Okay, yeah, the guy in the lake in the non-moving medium is always going to win the race. Okay, right. So with that picture in mind, you can throw some numbers to it and try that out. It's an old FCAT question or so much. Anyway, if you pace yourself in a race, you tend to win. The thing about this is that, okay, well, we know the Earth is spinning, the Earth is rotating, the Earth is also revolving around the sun, and they may have even known at the time, I don't know, 1880s, that maybe the sun was in motion around the galaxy, whether they knew that or not, they knew there was some kind of relative motion type going on. Okay? So they go, okay, well, if there is a luminiferous ether, Earth probably has a relative speed compared to that. Again, this is just hypothetical. They ultimately disproved this accidentally. Right? Okay, so we're going to set this experiment where we have a light source. We have a beam splitter. It's a half silver mirror that allows some of the light to go through, but also reflects it part of the way. We're going to put this at a 45-degree angle. We'll have mirrors at equal distances here and here. Right? And we're going to let this, I'm just following a single light ray. Right? Okay, the light ray splits. Part of it goes through and bounces off this 45-degree angle to this observer. Okay, and then part of it reflects initially and bounces off this mirror and then goes through and reaches the same observation point. Okay, now if there was such a thing as luminiferous ether and Earth's rotation and revolution around the sun had set up some kind of relative motion compared to that, then kind of like the guy in the lake versus the guy in the river, you would expect there to be some kind of difference in time for those two light rays to reach the observer, okay? And therefore they would be out of phase because light is a transverse wave. So they were hypothesizing something like this, and they were looking for like what is the relative motion of this luminiferous ether? Now, what they actually got was that the light was in phase, which was not what they were expecting at all. But okay, well, maybe it's the right time of the day or night. Maybe if we wait 12 hours and we're on the other side of the Earth, or maybe we just wait like a few months and we're on a different side of the sun, right? We should expect it. No, they always got the light in phase. And what this really represented, and this was one of a number of experiments that seemed to confirm the same idea, was that there was no such thing as luminiferous ether. Light can, in fact, travel through a vacuum. And furthermore, if you stretch your imagination a little bit, the speed of light is always the same, regardless of your frame of reference. Okay, so back in Newtonian mechanics, you could add or subtract velocity vectors. So if you're on a moving train and you throw a baseball, the speed that you consider the baseball to be going that you threw it is different from an outside observer who's watching the train in motion who could add the velocity of the train, right? Okay, but with light doesn't work that way. The speed of light is always the same regardless of your frame of reference, right? It's kind of what this leads to. Okay, so now that's 1887, right? So this experiment's sitting around for a couple more decades. Right, along comes Einstein in the early 1900s. Einstein's working as a patent clerk, so he's thinking very meticulously how mechanical things work. He's thinking about that Michelson-Morley experiment and some similar ones. Hey, he's asking questions like, what would it be like to travel along with a light beam? And he realizes something really bizarre and fundamental about the universe. And it goes like, okay, so let's set this special relativity train. Okay? By the way, if you've ever heard the phrase twin paradox, there's a whole story that goes with this. It involves like a guy in a rocket. I'm putting him in a train, but just go ahead and follow the story. Okay, so think, what if I had a guy inside a train car, right? And he puts a light source on the ground, has, say, like a mirror on the ceiling, and he just watches that light bounce up and down. You guys see this like pink box here, right? And let's just cut that story in half. So let's follow the light ray like from the source to the mirror on the top. It would go some distance. It would travel the height of that train, height of that boxcar, right? And distance is speed times time. We've got the speed of light times time. This guy's timing it with his clock. Okay, right? Okay, so we got that, right? Now, remember, one of the very first things I ever told you, let's go way back to probably August, has to do with relative motion. Guys, if you're sitting in the passenger seat of a car and you're blindfolded, can you feel if that car is going 40 or 50 or 60 or 70 miles an hour? No, you can't feel relative velocities, right? You can feel accelerations, right? You can feel it speeding up, slowing down, and going around a curve, right? So this guy inside this boxer, he doesn't even know if the car is in motion. Let's suppose it is. Let's say that this outside observer is looking in and he's watching the same story. So he sees the light ray not just go straight up and down, but move on this diagonal path, right? Except, so he sees it move at a different distance. It's still speed times time, speed of light times time, right? But hang on a minute. If both these guys could measure the exact same speed of light, right? Whether they do some kind of Michelson-Morley or some kind of Fizeau cogwheel experiment, they break out the cogwheel and measure speed of light, right? They both agree on what the speed of light is, but they disagree on the distances that the light went. Ooh. That means that they must perceive different what going on? Starts with a T. Time. They perceive two different times. So this is what Einstein puts together, is that when two guys like start out in the same frame of reference, and then one accelerates to a different speed than the other, that they perceive different passages of time. right? Now you can do just here. Does this look like Pythagorean theorem right down here? C squared equals A squared plus B squared sort of deal, right? Do you guys see a nice right triangle here? Nice right triangle. You guys see it? Right triangle. You can all you do is Pythagorean theorem, right? And you can do a little algebra shuffle and get one guy's time in terms of the other guy's time. So the red T naught is the guy inside the train. Or if you did with twin paradox, you replace the train with a rocket, you can call this guy rocket twin, right? And then the green solid T without the subscript is the guy who's just based on the ground. I might call him earth twin. Say you had earth twin and rocket twin. Rocket twin takes off in a rocket and flies like close to the speed of light, some relativistic speed, right? Okay, and then so now you have a comparison there 2 times, and it depends on how fast one guy's moving compared to the other guy. Right? Now you have to accelerate to make this work. Right? So all right. And this whole square root is called Lorentz factor. So let's sort of follow this. Let's say that they were both not moving relative to each other, both not moving. Wouldn't this v be 0? Guys, what is 0 squared? 0. Divided by c squared is 0. What's 1 minus 0? 1. What's the square root of 1? 1. What's t naught divided by 1? T naught. Okay, so t equals t naught. Okay, so what that means, this is something called the correspondence principle, which is that if you come up with some fancy new theory about how everything's supposed to work, not only does it have to be able to explain new things that the old theory couldn't explain, in this case, Newtonian mechanics, but it also should be consistent with the correct outcomes of the old theory. And Newton didn't know anything about these, what are called time dilations. And this pretty well confirms that. This says, hey, if this v is 0, or even just much less than c, right, then these two guys always agree on how much time has passed. In fact, if you plug in the escape speed of Earth, which is probably as fast as anyone's gone relative to anybody else, right? Let's say like Apollo mission, like headed towards the moon. The escape speed from Earth here, this is still a tiny, 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 tiny number. And this whole denominator basically goes to close to 1, right? But if you move at what's called a relativistic speed, let's say like a good fraction of the speed of light, then what you'll see is that the time passage for the guy in motion that accelerated to become in motion is always less than the guy who stayed on Earth. So in the twin paradox experiment, this is really fascinating. You just go home, look on Google or YouTube and type in twin paradox, and you'll see some cool stuff about this, right? This guy in the train, I'll call him rocket twin. He might be blasting around inside a rocket, like close to the speed of light for like a year. And he comes back and says, okay, a year has passed. And he finds his twin brother, and his twin brother says, it's been 10 years. Like, where have you been? Right. So they disagree about how much time has passed. Right. Okay. So if you think about it a bit, okay, so here's just the time dilation, right? Copy pasted right here. There has to be more going on than just that. Let's say here, let's say, for example, there's a star that's like 1,000 light years away, or let me change it. Let's say 100 light years away, 100 light years away, right? We want to get to that star, that star system, 100 light years away. Well, if you took off in a rocket, and let's say you went close to the speed of light, and somebody on Earth was watching you through a telescope, from their perspective, close to the speed of light, 100 light years away, it should take you 100 years to get there, right? To get to that star system. But remember, if you're inside the rocket, the fact that you're moving so fast, you don't perceive as much time has passed. Maybe to you, only like a couple of years have passed, right? So if that's true, and you reach the star system from your point of view in like a couple of years, that effectively implies this very bottom equation. There's some kind of length contraction. So the star system appears to get closer to you. Now, there's a lot of fun stuff you can do with length contraction. I'm giving you guys the crash course on this. But these effects you can actually see in real life too, like with particle physics. Scientists see these things all the time. Like there are certain like half-lives of radioactive particles that if they're on the move really fast compared to us, they like tend to last longer, right? You see these length dilations. There's also this momentum dilation. So you guys know momentum is mass times velocity. Well, that's the Newtonian version. Momentum is mass times velocity. But in Einstein's version of physics, it's really rest mass times velocity, but you still have to divide by this Lorentz factor. So if you get moving at a relativistic speed, these particles appear to gain momentum. And this is also something that particle physicists see all the time. You guys know Large Hadron Collider? It's a huge particle accelerator over in Switzerland. Actually, it's so big it actually crosses underneath the border with France, and they smash atoms together. They get these atoms moving at like near the speed of light. It's like 99.9 something percent the speed of light. And since they keep them in a like a circular orbit, they have to steer these with magnetic fields. But if they're getting them moving at these relativistic speeds at 99.9 something percent the speed of light, these particles appear to gain momentum, so they have to crank up that magnetic field strength to keep them like in a circle pattern. So if they put in like a gram of material and they get them moving, it might look like they have like 20 or 30 or 40 or 50 grams of material going around, right? It appears that there's more momentum than there actually. Okay, so these effects do show up. Oh, I want to give you guys another example of time dilation that is actually applicable to that you've actually used. GPS on your phone, GPS, right? Actually, you know what? Let me come back to that because I'm going to come back to GPS because there's one more thing I got to mention. Right. Anyway, here's a graph. Well, here's one graph. What this could look like. This could be relativistic momentum. So remember, Newton just said mass times velocity. Right? Einstein says, well, that's basically true for low speeds, but when you crank up near the speed of light, so the speed of light is like a limiting speed of the universe. Anything that has mass can never reach the speed of light, right? And its mass would, its momentum would head off towards infinity. The amount of time it perceives, like if you got really close to the speed of light, you would see the entire universe like flash by you, like in an instant. And you would also see length contract. Right? In fact, there's been a case made that from the point of view of photons, which actually do travel at the speed of light, that from the point of view of those photons, there's no such thing as time or space. If you sort of follow this logic, it gets kind of weird, right? If you ever see this Minkowski space-time diagram, okay, now I'm trying to represent 4 dimensions here on, say, a 3-dimensional axis on a 2-dimensional screen. So got to stretch your imagination for this. But you guys see like a couple of cones here. So what can affect what, sort of? What can affect what? Well, these XY axes, let's treat those as spatial dimensions, and there's 3 spatial dimensions, but I can always sort of represent 2. Right? And then there's also the dimension of time, like time is ticking along. So that's like the vertical axis here. You just conventionally, it's, I know we usually put time on the horizontal axis, but when you get to relativity and quantum mechanics, it switches. I don't know. It's weird. Let's just run with it. Okay. So we're putting time on the vertical axis. Now, also oftentimes they multiply that time by the speed of light to also represent sort of a spatial coordinate. So that the speed of light, anything's going at the speed of light, anything's massless always goes to the speed of light, will necessarily run along this 45-degree angle. You can make this a 45-degree angle if this vertical axis is also a spatial axis, which you can do by speed times time. Okay, but basically think of it as a time axis. Okay, so what could affect what? Let's say I want to send a message from here to Mars. Well, it's going to take several minutes for that message to reach Mars. It can't reach it instantaneously because of the limiting speed of light. If it did reach it instantaneously, then that would, well, break this, right? Right. So if I wanted to like have some kind of cause-effect relationship with someone who's over on Mars, right? There's definitely going to be a several-minute time delay, right? And vice versa, right? We can't affect each other instantaneously. Anything that you can affect is going to be basically inside this cone, right? So all of us right now could be at this origin point right here, and anything that led to us being here or becoming who you are or anything is always in this past cone. Anything outside the past cone is just too far away. Like that whole edge of space right there, that Hubble deep field, right? It can't really like affect you. Nothing that's going on there can affect you, right? That light, in a sense, can only because it's been traveling for like billions of years. So it's in the cone just barely, right? But anything that happened like yesterday or at the edge of space, right? And anything that you can affect can only be inside this future cone, right? You can't affect like Mars like 30 seconds from now because it's too far away, right? It's outside this cone. Right. All right. Oh, also from the special relativity, you can get mass energy equivalence. Now, Einstein's original version is, well, there's a whole proof. It kind of leads to this box here. E stands for energy, P is momentum, C is the speed of light, M is mass, right? But if you're at rest, the momentum you could call 0, and that just boils, and then you could square root both sides, and you get this E equals mc squared. This is the energy of nuclear reactions. Did I talk to you guys about nuclear energy one day? Nuclear energy? Did we skip that? Maybe. Reactors. Okay. Yeah, kind of forget exactly. Okay. Anyway, this is the equation of nuclear reactions. Nuclear reactions are different from conventional chemical reactions. That entire class you guys took called chemistry, there was always conservation of mass, right? Reactants equal products in terms of mass, blah, blah. And in nuclear reactions, that's not the case. If you run a nuclear reaction, say with uranium, say like U-235, the products you get actually have less mass than the reactants that you started with. And that change in mass is all converted to energy. And it's an enormous amount of energy, okay? About 20% of the energy supplying this room right now, the air conditioning, the lights, that projection, your laptops, came from a nuclear reaction. It's an enormous amount of energy. Okay? Right, so there we go there. You could also say, if you go from this box to this box, if you take the square root both sides, you can also get negative values. There's some kind of implication of that. I forget what it is, but Okay, now everything I've told you guys so far before the slide is all actually just one half of relativity. It's called special relativity, which is a theory of time, space, and motion. Okay. About 10 years after that, Einstein formulates general relativity, which also incorporates mass and gravitation. And so how Einstein's thinking about this is that space-time is like one fabric, one four-dimensional fabric, and it's warped by the presence of masses, right? And then so it's a alternate version to like Newtonian mechanics. For example, how about this, right? Like, why does the moon orbit the Earth? Well, the explanation that I gave you was a Newtonian explanation, which is, well, the Earth provides a gravitational force on the moon, and the moon has a sufficient tangential velocity, tangential speed, right? And so it'll like stay in an orbit that's elliptical, but pretty close to circular. Okay. Now that model works pretty well for a lot of cases. You can use Newtonian mechanics to like run the entire Apollo program, get to the moon and back. Okay. But there's some cases where it starts to break down. For example, if you look at the orbit of the planet Mercury around the sun, it doesn't exactly follow Newtonian mechanics, it has these weird perturbations. So Einstein proposes this and says, actually, all matter, including like the moon going around the Earth, is really just following a straight line, but the moon is just following a straight line in curved space-time. So the moon is still following Newton's first law of motion, right? It's just following like a curved path, right? And that actually could explain like the perturbation of the orbit of the planet Mercury and blah, 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 and all that too, right? Now, this also implies that like light could follow curved space-time, and light could also bend, even though light has no mass. Now back to Newtonian mechanics, say, well, hold on a minute, I thought to gravitationally attract you had to have mass. Photons of light have no mass, so how could that gravitationally attract? Einstein says actually they can bend, right? Light rays can bend according to because of gravitational effect. Okay. And this was one of the first observational experiments that was done to confirm this general relativity. Because of course, when this was proposed, there was a lot of skepticism. Is this real? Are we really going to overturn this Newtonian mechanics and replace it with this? Right? So there was a solar eclipse. I want to say it was 1919. I always forget the exact date, but you guys can look it up if you want. Right. So why do we care about solar eclipse? Well, replace the Earth here with the sun. And you guys know the sun, it has an enormous mass. That the sun is something like 99% the mass of our solar system, so something like that. So it would be big enough that the light could bend around it and you could like observe that. Versus if you're looking around like the perimeter of Jupiter or something, yeah, there's a lot of mass, but maybe it's not quite enough for what you would need to see this effect. So you can know exactly where the night, where the stars should be in the night sky, right? You can have a map, like here's where all the stars should be in the night sky. And then if the sun were to like cross across it, imagine like taking a magnifying glass, you get like a gravitational lensing effect, right? So the stars should be a little bit out of place. The problem is you can't see that during the day because the sun's so bright, you can't see the stars during the day, right? Except one case, and that's during a solar eclipse, during a total solar eclipse, right? That's why you care about solar eclipses. Right? Now, just by a complete freak coincidence of the universe, the sun has a diameter that's 400 times that of the moon, and it's also exactly 400 times further away than the moon. So when the moon crosses over the sun, it will just barely exactly cover it. So the sun and the moon have the same angular size compared to us on the Earth. Right? So that happens again. I think it was 1919. I think was the date. Right? Photographers took pictures. You could see the stars just around the perimeter of the sun. They took those back to the lab. They looked at them, measured them. In fact, they were exactly out of place. They were out of place exactly to the amount that Einstein predicted using his theory of general relativity. Okay? So this is a more exact version of what's going on. And again, just like correspondence principle for special relativity, this simplifies to Newton's equations when you have like non-extreme examples. Okay? So there we go. Right, relativity. Right, so that carries over with this here. I think I told you guys a little bit about dark matter. Here, let me scroll back, way back to last week. All right, go way back before all this electricity stuff. We're looking at this right here. Okay, I was here. You guys see what's called gravitational lensing, right? So this is a galaxy here, this ring. The galaxy is not actually shaped like a ring. It's shaped like a normal galaxy. But there's a blob of something called dark matter here, which we don't really understand what it is. It's like dark to our vision. It's also dark to our knowledge as to what it is, but it has some kind of gravitational effect. again, kind of like if you take a magnifying glass and you like, sweep it across, it'll create like a lensing effect. Right? This happens with gravity. So general relativity has been really good at predicting like why things look like what they look like in the sky, right? And sometimes you'll see like the same picture of a galaxy just like in 3 different places because it's being like lensed around, right? Like some spot of dark matter. In this case, it looks like a ring, right? So let's go way back to where we were. Okay, all right, here we go. Right, so there's something out in the universe called dark matter. In fact, there's if you run the numbers on it, the math, there's a lot more dark matter than there is even like ordinary matter, like all the stuff in this room that makes up the periodic table. Supposedly, I haven't run the numbers myself. I'm just telling you guys what I've read on the internet, where everything is true. That ordinary matter supposedly only makes up about 4 or 5% of the universe. About a quarter of the universe, about 25% is this dark matter, and about 70% is what's called dark energy, which is a totally different thing. Right. So here, let's get dark matter. What's the evidence for this? So if you look at galaxy clusters, right, there's clusters of galaxies, and there's like more attraction than there should be without this what would be dark matter. Right. Okay, gravitational lensing. I showed you guys that what's called an Einstein ring gravitational lensing effect. And also, if you look at the rotation of galaxies, if you just follow general relativity with ordinary matter, you would expect this green dashed line, right, for like how fast the stars should be going. Like, okay, this should like slow down the further away you get, kind of like a Kepler's law kind of idea, right? Right. But the actual observation is that the stars are actually traveling like the same speed, regardless of how far you out from the center. And that could be explained with the presence of this dark matter. Right. Now, dark energy is something else. This has to do with okay. Let's backtrack a little bit. The story. Let's go back about 100 years ago. A guy named Hubble was looking up in the sky, realized that almost all galaxies relative to us were redshifted. Redshifted means they're moving away from us. In fact, some galaxies are redshifted more than others. In fact, the further away they are, the more redshifted they are. And this led to the understanding that the universe is expanding. It's expanding uniformly. There's no center of the universe. It's just sort of expanding, like all, like, or you could say maybe the center is sort of everywhere. Right. So you can run the clock backwards. Just measure these redshifts and say, like, well, how far away, how fast are these galaxies moving relative to us? You can run the clock backwards to say, well, it looks like everything was at the same place, same time about almost 14 billion years ago. Sometimes you can round it to about that number. Sometimes say 13.7, 13.8 billion, something like that. Right. So the hypothesis for almost 100 years was, okay, well, there's probably something like everything started off together. All right, this is where the Big Bang idea comes from. And everything's moving away from each other. But if everything gravitationally attracts, then maybe the universe is going to end in a big crunch where everything just eventually pulls back together. And it's that, well, hold a minute. That's not the only possibility. Maybe that's sort of analogous to if you throw a baseball up and it comes back and lands in your hand. But you could take the baseball and throw it up fast enough to reach its escape speed and flies away forever. Maybe the Big Bang had enough energy for that to happen, but everything should still be gravitationally attracting. So that process should still be slowing down. If that will maybe able to reach an asymptotic size that's sort of analogous to some kind of orbital speed. And about 20 years ago, different teams of scientists around the world, independently of each other, set out to answer this question of, well, what is the ultimate fate of the universe? Is it going to end in a big crunch? Is it going to expand forever? What exactly is going on? And they all arrived at the same conclusion. And they all arrived at a conclusion that none of them were hypothesizing at all. And the conclusion they came to is this graph right here, that the size of the universe is a function of time. Not only is it expanding, right? It's actually accelerating its expansion. It's expanding faster and faster and faster. And there's no good theoretical reason for this to happen at all. Like why would this be? Like there is really no explanation for this. So right now, the term being tagged to this is just called dark energy. You can put it in this general relativity equation right here, right, as this expanding universe. So you can put it in as an energy term, right? They can quantify it mathematically. They can say 70% of the universe it accounts for. But like, what is it? It's a huge question mark, right? So here's a couple of mysteries out there in the universe. All right. Any questions about relativity? All right, let's move on to quantum mechanics. So quantum, this is about 100 years or so ago too. Now this starts off with, weirdly enough, ovens. Right? And scientists are looking at these ovens and they're saying, well, we know that light is a wave. We know it because of this Young's double slit experiment. You shine a light through two slits, it creates an interference pattern. What does that? Waves, light's a wave. Okay. So if you follow that, then if you look at the, say like the spectral radiance as a function of wavelength, according to this classical theory that light's a wave and only a wave, it should follow this black curve. So that if you're, say, baking something in an oven at these temperatures, right, like 5,000 Kelvin, for example, it could be really, really hot, then the light that's coming off that should like be crazy, blindingly bright, but it's not. It actually follows this blue curve. So here's the actual observation versus here's the classical theory. So there's this mismatch. So they start playing around with these ovens. They say, there's something weird going on here. 1887, this photoelectric effect, Heinrich Hertz realizes that the light that you can collect, think of this sort of like solar collectors. I'm sort of simplifying the story, but you guys know you can collect energy on solar panels, right? Right. So say like the energy you can collect is a function of frequency. I got 10 to the 14 hertz here. If it's below a certain cutoff point, and for this particular experiment, I've got these numbers here, but let's say like 4 times 10 to the 14 hertz, you're not going to collect any light. According to classical theory, well, if you just pump up the intensity, then that should make it brighter and you should get more energy, and maybe you should get energy that way. But you'd never get energy that way. You could get energy if you increase not the intensity, but the frequency, which was not expected. So this is all weird. So this is weird. This is weird. Something's not adding up. Einstein comes along. The same year that Einstein proposed special relativity, he also explains this photoelectric effect. And actually, Einstein's explanation for this photoelectric effect is what won Einstein a Nobel Prize in physics, right? Weirdly enough, none of that relativity stuff that he's most known for won him the Nobel Prize, but the explanation of this did. And Einstein says, hey, light is not only waves. Light has this dual nature, and light is also particles. And I'm going to call these particles photons. And it has to do with this. If you say like double the frequency, you're like doubling the number of photons. And these photons are like packets of energy, and that would double the energy. And that could actually explain this photoelectric effect, right? Triple the frequency, you'll triple the energy. All right, there you go. All right, so the slope of this line, by the way, I'm labeling h. That's called Planck's constant. Tiny, tiny, tiny number. Guys, 10 to the negative 34. That's crazy small. I think it's the craziest number we've dealt with until you get to these other numbers that are also crazy small. Planck length and Planck time. So you guys know how if you look at a screen and it looks like a fluid picture, maybe this video playing looks like a fluid video. But if you get in close enough, it's really just a bunch of dots. In fact, it's just red, green, and blue dots, right? RGB. So what about the universe at large? Is the universe at large actually like fluid, or is there like some like quantized sort of pixelated version of the universe? Well, according to quantum mechanics, there's the smallest length you can talk about that makes sense, and there's also a smallest unit of time. Now these are crazy, crazy, crazy small numbers. In fact, just to put it in context, there are more of these Planck 10 to the minus 44 seconds. There's more Planck time in a single second than there have been seconds since the Big Bang, right? Since all the seconds that have existed in the universe. So we're talking about crazy small intervals of time. But interestingly, if you divide this length by this time, this Planck length by this Planck time, you actually do get the speed of light, which is also one of these fundamental limits of the universe, right? So here we go. Got Planck constant, Planck length, Planck time. Right? There's now we're running into limits about what we can get to the universe. The universe is sort of quantized now. There's a limit to what we can fundamentally know about the universe. Now, this wasn't true back in Newtonian mechanics. Back in Newtonian mechanics, you could know the position of a particle, you could know the momentum of a particle, you could know its mass, its velocity, you could write down equations and predict exactly where all these things were going to be. But that's not true in quantum. In quantum, there are these limits you run up against. And these are like fundamental limits in our knowledge, like they're just baked into the fabric of the universe. So it's not a matter of like, oh, well, we just can't measure, but if only we could measure. No, it's like you aren't even allowed to know precisely where a particle is and also its momentum, like it's which includes its direction of motion. Do you guys know a YouTube channel called Veritasium, maybe? Yeah. Okay. He actually, if you type that in and type in a Heisenberg uncertainty, he actually does a Heisenberg uncertainty experiment. He shines a laser through a tiny slit, and he makes the slit smaller and smaller and smaller. And on the back wall, you see the spot getting narrower, which makes sense that would. But at some point, it starts spreading out, because at some point you get too much information about exactly where those photons of light are, and so your knowledge about the direction of their motion has to be limited. Now, this is still a tiny number. Like Planck's constant is like, what was that? 10 to the minus 34. right? Joule seconds. Okay. Okay, so this is still crazy tiny, but there's like a limit to what you can know here. Okay. This is a French guy, De Broglie, who starts thinking about this duality and says, I wonder if duality applies to more than just light. What if it applies to other particles too? And so, all right, we got a small proof here. It says, here's how you can describe the wavelength of any particle, right? Mass times velocity. Well, that's properties of particles. Lambda, that's wavelength, that's properties of waves. Here's H Planck's constant. Now you can quantify the wavelength of any particle. Now, maybe this wouldn't be super significant unless maybe you had something where the mass was tiny enough. Now, what's a particle that you guys know has a tiny, tiny, tiny mass? What's the smallest mass particle you know? Okay, and hydrogen is composed of what? Proton, neutron, electron? Sometimes just protons and electrons. Which one of those has by far the smallest mass? Electrons. Electrons, right? Right. Yeah, so what is I should know these mass ratios, but yeah, the electron is tiny, tiny, tiny mass, even compared to protons. So what if you started thinking about electrons here? Electrons. You plugged in the mass of an electron here. Well, that would imply that maybe the mass an electron has a significant enough wavelength that its wavelength properties actually matter. In fact, this sets up all of chemistry. Do you guys remember this energy levels? You guys remember this from chemistry? Like the orbital levels? Okay. So when you learn the structure of an atom, you're probably taught, okay, well, there's some kind of nucleus that has your protons and neutrons, and then the electrons orbit around it, maybe kind of like planets in the solar system. But that analogy is not perfect. And one of the reasons it's not perfect is that, well, planets could be at any location relative to a star, right? They could orbit it anywhere. You could just calculate what the tangential speed has to be. But that's not true for electrons. Electrons have to fill certain orbital shells, certain energy levels. In fact, they have to fill them in a certain order, right? So this falls out of the fact that electrons have certain wavelength properties. In fact, electrons are actually arguably more like waves than they are like point masses at all, right? So like to make it around, they have to fill like a certain number of wavelengths. Now, even this is a simplification. If you look at the actual orbits of electrons, they're all like weird in 3 dimensions and they're all weird, funky shapes, but just get the idea down, right? That electrons have more wave-like properties than they do particle-like properties. And this explains here, this sets up the entire periodic table, right? Why is there a periodic table? Why is there an organization to it, right? Why is it that like all the noble gases are like in one column, and then column by column, there are certain valence electrons that tell you exactly how each atom is going to chemically react? Oh, well, it all comes back to this, which all comes back to this, okay? Okay, ooh, double slit experiment. Okay, here's a really weird one. Now this is a super simplified cartoon version of this, but if this really fascinates you, then please do look more into it. Let's go back to that Young's double slit experiment. Now here I have an electron going through, could be photons, could be electrons. Yeah, anyway, you have some small particle going through this double slit. Now, normally what you see out of that is an interference pattern, which indicates that it has a wave-like property. That's what waves do. Waves create interference patterns, right, when you shine through double slit. But if you have some kind of detection equipment, and here I'm just representing it with a cartoon eyeball, but there's like a whole experimental setup with this. If you have some kind of detection equipment to determine exactly which slit does a particle go through, and you can actually have that knowledge, then the particle actually changes its behavior, and it goes back to behaving like a particle. Now, this is leads to something called the measurement problem. The measurement problem here, like all the experiments that we've done in this class, there's been an assumption that's been going into them, which is that if you want to know how something in the universe works, all you have to do is create a model of that universe, right? And then be an outside observer and make some measurements, and then you can go crunch the data and make some calculations, right? So let the car go down the incline. It's going to do what it's going to do, regardless of whether you're observing it or timing it or not, right? Does a tree fall in the forest, or if the tree falls in the forest, does it make a sound? Okay, well, maybe that seems like a silly question. Like, why would it depend if there's an observer or not? Well, in this experiment, the fact that there is some kind of detection equipment that's making a measurement, that actually changes the outcome of that experiment. So at least something called the measurement problem. Right. There's also a related idea, famous example in quantum mechanics called Schrodinger's cat. I may have heard of this. So one of the early quantum physicists, this goes back to the 1920s, 1930s, was a guy named Erwin Schrodinger. I should have a separate page for a separate slide for a Schrodinger equation. Let me tell you guys about Schrodinger's equation a little bit. Schrodinger's equation describes the existence of a particle. Now, existence of a particle, it's not like Newtonian mechanics, like there's just a baseball sitting here. We know its mass, its position, its velocity, right? It's not like that. Particles down at the atomic scale exist probabilistically until you measure them. And then that wave function of their existence collapses to just one reality, and they're either one place or they're not. And it's probabilistic as to where they're going to be. And scroll back a little bit, right? They tend to like fall into like certain orbital locations, right? You could show this with Schrodinger's wave equation, right? So there were a lot of these weird. I mean, quantum mechanics get so weird. There's famously the saying that if you say you understand quantum mechanics, then you don't. Like nobody understands quantum mechanics. It gets so bizarre. So some of the things he was looking at the time, he said, "Hold on a minute, this has this weird implication," and he sets up this whole story with this cat in the box. And he says, "Here's why everything that we're seeing can't be true." He was actually trying to sort of like push off and debunk some of these ideas. But people saw this story with the cat in the box, other fellow quantum physicists, and said, "Actually, you know what? You're raising a good point. Actually, that is kind of what's implying here." So how does the story go? So let's say you have a closed box. When I say a closed box, this observer here, which I'm again representing with a cartoon eyeball, you can't see inside the box, you can't detect inside the box, you can't feel the box. What's going on inside this box is completely unknown to this outside observer, right? I should say to you, the story I'm about to tell you guys is a complete hypothetical thought experiment. No one's ever done this, and you sort of can't do this experiment. It would, like, by doing it, you'd sort of like be undoing it. So it sort of like can't be done, right? But let's take radioactive particles for example. Radioactive particles. Now, not all particles are radioactive, but ones that are have a certain half-life associated with them. Now, the half-life could be anywhere from a tiny fraction of a second to like thousands or tens of thousands of years. For example, here, go off a little bit of tangent, but just to set this up a little bit more. All of us right now have a certain amount of carbon in us, right? We all have carbon in us. That's one of the building blocks, right, of life. And most carbon in the world is what's called carbon-12, has 6 protons, 6 neutrons. But there are a couple of isotopes of carbon that are not carbon-12. One of them is called carbon-14, which has 2 extra neutrons. Now, carbon-14 is radioactive, but on a scale of like 5,700 and something years, that's its half-life. So if you start off with like 8 grams of carbon-14, you wait 5,700 years, now you're down to 4 grams, and the other 4 grams have decayed into nitrogen. You wait another 5,700 years, now you're down to 2 grams. Wait another 5,700 years, now you're down to 1 gram. Now, those are big numbers for carbon-14. All of us right now have the same proportion of carbon-14 in us, and we're all maintaining that proportion as long as we're alive. In fact, all living organisms, that's true. You'll always maintain the same proportion of carbon-14 as long as you're alive. Now, as soon as you die, that carbon-14 starts to dissipate, and that level is not maintained. That leads to carbon-14 dating. So if you're ever an archaeologist and you go stumble across some old ruin, let's say you like dig up an old mammoth, right, up in the tundra, like, hey, I wonder how old is this mammoth? You can take a sample of it back to the lab, say, well, how much carbon-14 does it have? And if it has like a quarter of the carbon-14 that it should have had it like died yesterday, they say, oh, well, that's 2 half-lives that have passed. That's 5,700 years. Hey, this mammoth that I just dug up from the ground is probably a little bit over 11,000 years old, right? That's how you can do carbon-14 dating. Okay, but get back to here. When does a single atom of this carbon-14 decay? Well, that's a matter of probability. So suppose it had a half-life here. Let's say a half-life of like an hour, okay, for whatever particle this is, and you leave it alone in this closed box. Now, if it decays, it's going to set off this whole chain reaction where it trips this poison, which would kill a cat. So we put all this in a box, and we wait an hour. Now, after an hour, you might say, well, probabilistically, there's a 50% chance it's decayed and killed the cat, and a 50% chance that it hasn't, and the cat's still alive. But from a quantum mechanics point of view, that particle always exists in a superposition of states until you observe it. So until you open the box to make an observation, to make a measurement, it's both decayed and not decayed, which implies that the cat is both dead and alive simultaneously. The cat is also in a state of superposition, even though the cat is macroscopic and we're not. But this opens up a question too of like, well, if the cat is an observer, and if it's still within a contained box, are we sort of in a contained box? Do we need some kind of outside observer to like make us exist? Right. So it also opens up a bunch of weird questions. But there you go. There's quantum mechanics. I have a few slides left, but I think the bell's about to ring here. All right. So there's a good pause point. I'll see you guys. I think tomorrow for about a half hour. Yeah. So see you guys then.